It is now started. Okay, so everything from here on will be recorded. All right. So I quickly talked about, parameters and return values on Monday, I mean Tuesday. And so what we'll do today is to kind of continue how we are going to use the stack for functions. So today's focus is going to be on local variables. So we're going to be able to see local variables in conjunction with um, parameters in the context of functions. Okay, so we'll go ahead and take a look at some C programs first. Okay, we'll make sure the C programs function as they should, and then we'll try to implement the same thing in assembly language. And everything that we are now talking about has to do with the caller callee agreement. So this is a really important document. So I just kind of opened it first. I think I got it open before. Yep, there we go. All right, so the stack operation or the caller callee agreement is one of the most important documents for this part of the semester. One thing that you might want to consider doing is to go all the way to the end and then go to this link here, view the source document. And once you get there, it is really just a GitHub link. You can download the whole thing. You can download the raw file, which is just going to be a markdown file, and then upload it to Gemini. Okay. I would create a Gemini gem, just for this class so that you can collect all the documents that are related up to that particular gem. If you don't know what is a Gemini gem, you can learn about it. Okay, you just ask about what is a Gemini gem in Gemini. So you can ask here, what is a Gemini gem and how I can use it in a class that makes use of OER content. So OER stands for Open Educational Resource, which is basically what I use in this class. Okay, so the copyright, it's not like there's no copyright, but the copyright does allow you to upload the content to something like, Gemini. So just press the enter key, and let Gemini explain how Gemini Gem can be useful in a class that makes use of OER content. So we'll go ahead and take a quick look because I think this might be helpful. Okay, some of the material from here on can be a little bit difficult to understand, so having an AI assistant to help you can be helpful. So you're gonna I'm not going to read the whole thing to you. I mean, I gave you the prompt. You can just go ahead and use the prompt yourself, read about it, interact with the chatbot, so we can get more information of how to best use the Gemini Jam. The only downside of using this is, guess what? Your second exam and your final exam, they're both on paper. You cannot use AI in your exams. So the best thing you want to do is to use the AI to help you understand the material so that by the time you get to the exam, you won't need the AI anymore. All right. So do we have any questions about, how to use Gemini Jam? Yep. You can use Gemini better. I think Gemini does a fairly good job. I have not exhaustively tested, Gemini, but I think it does a decent job. I think I might have made a jam already. So let's go ahead and just make a jam really quick. So we'll go to Explore Jam and make a new jam. And this new jam, I'm not going to release the jam, so I'm just going to play with it. This is just me playing with it. So we have to give it a name. Okay, so I'm gonna say this is my CISP 310 TA, and the description is teaching assistant of CISP 310. You guys, can do it entirely differently, depending on how you want to do it. So the instructions is the most important part, okay, because you're telling the AI what is the role that the AI really should take on. So in this case, I am going to tell it about, um, let's see, instructions. I want to say that you are a teaching assistant of the assembly programming class. Um, okay, four. Okay, fine. Proposition. Use the included knowledge files to answer questions. Okay, there we go. So I'm not putting a whole lot of restriction on this one because I'm not releasing it anyway. And then in terms of the knowledge, this is where you upload the files. Okay, you can have up to 10 files. That's it. So what you want to do is to make sure that you upload you can concatenate files, by the way. So if you go to this module, you go to download here, and it just download as one file. And you might want to name the file after the module name, which is 0372. It's just a text file with an extension of MD because Markdown is just plain text. So in the Gemini, if you only have one single file, you can just go ahead and upload it. If you have multiple files, you can concatenate. So other files that you might want to also include would be the earlier discussions, and anything in here you can just kind of upload. Okay, we have the stack operation, so you can go ahead and download that one too. So we go to the compile one, we can download for this class, right now, this one is more important, so I'm just going to go to this one. I'm just showing you kind of, like the steps of how to do it. You don't have to do it now, but so here we go to download again. Okay, this one is, what is the module name? Um, 304, so 0304. Download this one. The opcode table is really important too. So you probably want to download the opcode table one too. So with this one, you just download it as a regular HTML file. Okay, that should be okay. So we download this one as opcode table dot. Why does it want to download as a zip? Oh, because there are two sheets. Why does it have two sheets? I only need sheet one. All right, so let's go ahead and download just one of them. Oh, I know why. Because in HTML, it wants to, kind of concatenate everything. So we can, we'll pick. It can also read PDF, by the way. So I can give it a try. Just download the PDF. So there we go. Export. There we go. So this is the opcode table PDF. All right. So I'm just gonna give it a try now. So go to, for me, it is a command line kind of thing. You guys can use whatever tool you're used to. I'm just not, okay, where's my, there we go. Okay. So what I'm gonna do is I go to my temp folder and I'm going to concatenate the two markdown files into one. And I have no idea where I downloaded those files. Where did I put it? Oh, okay, put it into the wrong folder. That's okay. You can go to that folder. Okay. So what I do, you don't have to do it this way. So I'm just going to do it this way. So I am going to concatenate the two markdown files, cat 0304, 0372 into one single combined file. I just call it cisp310.md. And now we can now go back to my Gemini Jam and upload the file. So we go back here, we upload. I think one is um, cisp310.md. Okay, so I upload that one. And the other one is the opcode table. So we're going to upload the other one too. So opcode table right there. All right. So that now that I have uploaded both of those, I can now save. Okay, there we go. And after you save it, it will ask you want to start a chat. So this is where we're gonna give it a try, right? Okay. So I will ask explain how parameters return address return spell out address and um, local variables are organized on the stack. Okay, it's really that easy. And you can put more stuff, into the markdown file. I just used, two of the many markdown files from the Canvas shell. So we'll see. I'm using the 2.5 Pro model, which I think is better. It does take a little bit longer. So it has an explanation. The organization is managed by a set of rules called the callee agreement. Okay, well, it knows that we are using register D as the stack pointer. It also knows what instruction, because I have snippets of those instructions. So the caller's job is to do blah 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 and so on. So now you can even potentially give it a program in C and see whether it can generate the assembly code. So now you can say, can you generate the code TTP ASM code for the following C code, and I'm using the code block here. Okay. U in 8 underscore T sum U in 8 T X U in 8 underscore T Y, and then return X plus Y. I'm just testing it right now. Okay. But remember, don't over rely on the AI, okay? Because if you over rely on the AI, you may not be able to answer the questions in the exams. So only use this as a tool to help you understand the material, but not so much to have it to do all the work that you need to do. So we'll go ahead and see what the answer is, okay? Wow, actually it does it the same way that I would normally do. Subtract it. This is all correct. This is okay. It's not done yet. Is it done? No, it's not done yet because it still has a that button. But so far so good. Okay, so this is not bad. Okay, I think it's actually not bad. I just want to demonstrate it as a resource. Okay, so that you guys know that this resource is available to you. I'm not going to stop people from abusing the resource because I can tell from the final exam and also the second exam, okay? So do not overuse this, okay? Use it, as necessary to explain the concept, but not so much to have it to do the work for you. All right? And it even comments everything. I mean, that's pretty good. All right. So with this said, I'm going to start a new program, okay? Something that will illustrate all three concepts. The return value, we are going to talk about the local variable and parameters. Okay, so are we doing okay so far with that? All right, cool. So we are going to go back to the temp folder. I'll talk about a simple program. Okay, so we'll say sample1.c pound include standard integer dot h u in 8 underscore t. So what I'm going to do is a pre-increment, or well, let's make it post-increment. So we'll make it a post-increment operation, but in this case, it's going to have two parameters. The first one is going to be a pointer to the integer that I'm supposed to change, because it's a post-increment. So I'll just call this PTR. And then the second one is by how much. Okay, do we want to post increment? So this is basically, I'll just say how much. All right. So in here, we're going to have a local variable. I'll just call it old value. And then we say old value. We take a snapshot of the current value of wherever PTR is pointing to. And then we are going to increment whatever PTR is pointing to by how much. So we're going to say, whatever PTR is pointing to is going to be increment by exactly, how much as a parameter is specifying. But what I return here is just the old value. Okay. So do we have any questions about the function itself? Post inc as a function. Do we have any questions about any of these lines of what it is doing, or are you seeing any construct that you have not seen before in CISP 360? So we're all good? Okay, so we understand all three lines of code, including the return. Okay, so now we're going to go to main. Okay, so main this time is going to have its own local variable, and in fact, we'll give it two. So u in a underscore t, we'll just call these x and y. X is the one that's initialized with a specific value. We'll just make it 67 for no particular reason. And then Y is going to be the result of post inc. And then we specify the address of X along with how much. Okay, so let's just say that we want to post increment X by 13. Okay, so it should become 80 in this case. So return 0, and that's my entire program. So are we doing okay so far with just the C code, including everything in main? We good? Okay, all right. So we are gonna, translate this code into assembly once we know it runs in C. Okay, so we'll make sure that this runs in C. But before we do that, okay, we need to know the outcome of the program before we actually try to translate it, or even before we run it in C++ or in C. So what do you think is going to be the value of X by the time we get to line 15? Hmm? It will be, it's going to be 80. It's going to be 80 because we are passing the address of X as a parameter to PTR, and then inside the function postinc, whatever PTR is pointing to is increased by how much, and how much is just a literal constant of 13, right? So that means whatever X had will be incremented by 13 or increased by 13, and therefore X is going to have a value of 80, 80 in decimal. But on the other hand, the return value is before it's captured, it took a snapshot of the value of whatever pointer is pointing to before the actual increase. So that means old value as a local variable should be just 67, and that is the return value. So as a result, y is going to be 67. So the end result is y should have a value of 67 and x should have a value of 80. Are we good so far? All right. All right. So now we're gonna test run this program, making sure that it is correct. GCC-C-O sample1 and then we just go ahead and run it in the debugger. Okay. The If you don't run in the debugger, okay, there's no way you can tell what's happening in the program. It has no cout, no printf, nothing, right? So by the time we get to line 15, we just want it to stop, run the program, and now we say, okay, what is the value of x? It is 80, and then we look at the value of y. It is 67, just as expected. So I'll be doing okay up to this point. Are there any questions about the C code? Because we cannot really talk about the assembly code unless we understand the C code itself. So is there any line that you want me to explain any further? This is a good test of how much you got out of the CISP 360 class. Are we good or not? We good? Okay. Any questions from anyone? No questions? Okay, well, all right. So we're gonna go ahead and implement this program in assembly now. Okay, so the typical thing that I do is to copy this to sample1.ttp.asm, and then we'll go ahead and just get started with the assembly language file. Just go ahead and insert slash slash in front of every single line, and then we can interleave our assembly code with the C code. So I usually start with a no op, because this is actually required to use Reefer Spider. So we have to start with a no op instruction as the very, very first instruction. This one is kind of optional, okay? I put it here just so that I make it clear that we are initializing the stack pointer to be the highest location plus one, okay? Because the highest possible location is 255 plus one, turns it back into zero because we have 8-bit numbers. And then this time I'm going to use, I will consider main as if it is just a normal function. So I'm going to call main. So let's do this one. Okay. All right. So have I explained what is the dot in this class? I think I did, but I could be. Nope. Okay, that's fine. So let's go ahead and take a look at what the dot six plus is doing. But before that, we are going to have to pick a little stub out of main. So this is the entry point of main, and we are going to um, have the return code for main, LDBD, increment D, and then JMPB. That's the usual return. These three instructions are what we use for returning. So that was talked about last Thursday. Okay, so this is a topic from last Thursday. So that means if anyone is looking at these three lines of code, line 24 to line 26, and have no idea what they do, it is time for a little bit more studying. I'm not kidding. This is serious, okay? Because with this class, at this point, we are building concepts on top of concepts every single class. Okay, so that means you have to catch up with the content as much as possible. All right. So getting back to this part here. So the normal way we do, we specify the return address is not like this, right? So the normal way we do it, okay, let's comment out this one. The normal way do it is we put a label as the return address. So we'll say this is return address one. And then over here, we use an LDI instruction to specify, okay, let's put return address one or the value of the label into register A. So this is a typical way for us to call a function. So once again, okay, this is something that we talked about last Thursday, but no later than last Thursday, because by this Tuesday we were already talking about parameters and the return value. So if line 4 to line 8 does not look familiar to you, it's basically a reminder that you might need to do some more studying. Are we good so far? All right. Okay. So let's just assemble the program like this, okay? We can run it, we can assemble and run the whole thing because it does run, okay? We'll just kind of check out what it's going to do, and particularly what is the value of the label return address one. Okay, so we're gonna do just that. Save first, and then use my other prompt to do the actual running, so I don't have to flip back and forth. Okay, so we'll submit. This is called sample1.ttp-asm. Okay, so we'll give it a little bit of time to do the assembling, but I pretty much just need it to be assembled. So I don't even need it to run for the time being. Okay, so that's all we need. We go to the assemble tab, which is here. So now we can actually see what the program looks like. This is the line that I'm talking about, which is line 4. So line 4 has returned address 1, as my immediate value, which is the second byte of which is the byte right after the opcode. 6C is the opcode of LDIA, and then the immediate value, which is return address 1, is 09. And it does make sense because 09 is in fact the address of the halt instruction, which is exactly the instruction that we should continue execution after main is done. So is that okay so far? Okay. So now we go to the analysis tab to really take a look at how the program executes. And oh, okay. I guess I goofed up somewhere because in main it is not. Oh, right. Hmm. Well, the program doesn't seem to be working, so let me see why it is not working. It did push a 9 on the stack, it continued execution in main, and then it lost track of what is in main, which is kind of mysterious. Yep, the program definitely did not work the way it's supposed to. Huh. and in it went to location 616. So in the assemble tab, 16 is not even in the program, so it went to the wrong place. Okay, let me try it one more time. I encountered something like this the other day, so just to be sure, I can give it one more try. All right, go to the analysis tab. And this one, it worked okay. So for some reason, okay, sometimes it just doesn't sync up, or maybe the page just needs to be refreshed. So anyway, on line 7, we have a JMPI to main. The one thing that we push on the stack this time happens on line 6, and we are writing the 09 to location FF. This is how we push the return address on the stack. By the time we get to main, which is line 27 or line 26, we retrieve the return address into register B. Then we increment the stack pointer, so it goes from FF back to 00, and then we do a JMPB, which is using whatever register B has to continue execution, which is at location 09. And then at that point, we get to the halt instruction, and then the whole program stops. So the program is doing what it is supposed to. Is that okay? All right. If you have any questions, do not hesitate to raise your hand and ask your question. Or if you think you need more time to formulate your question, you'll do the same thing. Raise your hand and just say, okay, can we slow down? I need some more time to formulate my question. So all of those is okay. So when we get back to the assemble tab, we want to look at, okay, why is this 9? Okay, well, that's because 6C is at location 03. So the 09 is at location 04, 05, 06, 07, 08, and this is 09. Are we doing okay so far? Okay, so that means, hey, it looks like, if we keep the same template of code, I may not need a label because it looks like the number of bytes between the 6C and where the return is supposed to go, which is over here, that distance is always going to be the same, which is the 09 minus the 03. Are we understanding? Do you understand what I'm talking about? Okay. So that means, maybe in the program, okay, I can just do something like this. Okay, so instead of doing this, we can now do something like this. So the dot 6 plus it just means dot plus 6. So now the question is, what is the dot representing? So as it turns out in TTP-ASM and also in many other assemblers, the dot is representing the address of the opcode of the same line. So in this case, it is talking about the location or where the LDI instruction is located on line 3. So getting back to the assemble tab, okay, let me assemble this one first, so that you can see how it assembles. So we'll go ahead, make sure we save the code, and then we just reassemble it. I don't need to run it this time, but it's going to run exactly the same way, so we cannot really tell the difference when it runs. So we only need to know about the assemble. You can see that it's exactly the same as last time because this dot over here, is actually representing the address of the opcode on the same line. So the LDI opcode is at location 03. So when you add 6 to it, it becomes location 09. Is that okay? So now the question is, why did we want to do it this way? I think that was the last question of the lab on last Thursday. Okay, most people did not get everything right. They got most of it right. The reason why we do it this way is because this way we don't need to rely on labels. So what is so bad about using labels? The problem with using labels is if you use the wrong label, because if you have a lot of function calls, you are going to have a lot of label definitions because every point of returning has its own label. So if you accidentally use the wrong label when you specify the LDI instruction, as long as that label exists, the assembler doesn't care. So you can be using the wrong label, and then if you do use the wrong label, then the callee is going to return to the wrong location, and it will just throw your program into a big mess, which is not good. Okay. But when you use this method, we are not using labels. Okay, you can basically essentially can copy and paste this code as long as you keep the same template all over the place, and it will still work. So that's the advantage of not using labels. It doesn't save you any space, okay? It still uses exactly the same number of instructions, but it saves you from having to define a label, which is not a big deal. The assembler can handle it, but it also saves you from the potential problem of using the wrong label. That is the main idea behind using .6 plus. Now, .6 plus is a postfix notation. We specify the things that we want to add, then we specify the operation, which is the add operation. So are we doing okay so far with these concepts? So you use a label. Well, you can use this method as long as where you what you need to specify is relative. You know the relative offset in terms of bytes. Every time you know the offset is constant, you can use this approach. But when you kind of stuff in between and kind of varies, then you probably want to use a label. Yep. All right. So now that this part is done, we can now proceed and talk about main. So main has two local variables. So now the question is, where do we put all the where do we put all the variables? Post inc has one, main has two. So the question is, where do we put all the variables? Well, I guess you don't have to kind of think too much. They're on the stack. Okay, so if they're on the stack, then they are also going to be somehow related to parameters because we know parameters are on the stack. That's what we talked about on Tuesday. We also know the return address is on the stack too because that's also what we talked about. That was from last week. So now the question is, if local variables are also on the stack, then where are they? Well, this is why you kind of need to read the module because it is all kind of explained in the module. So the module that I'm talking about is this one. So the stack, how the stack is going to be used is, okay, there are a lot of examples. So this would be the best picture of what it looks like on the callee side. So if you're on the callee side, the return address is at some point in the memory. The below the return address would be where the local variables are, and then above that would be all the arguments. So that's basically this entire thing is called a call frame, okay, or otherwise just simplified as a frame. It provides the entire context for a function to operate. Because what do you need in a function? You need your local variables, you need your parameters, and you also need a return address. So this is called a frame. It contains everything in the context of a function. And this is also how everything is relatively located. So if you, yeah, go ahead. It varies. So it can have one single byte if you're talking about a function that has no arguments or no parameters and no local variables. In that case, you only have one byte, which is your return address. If you have parameters, then the parameters will take up some space. If you have local variables, the local variables will take up some space too. Mhm. All right. So let's go ahead and take a look. We'll take a look from the main perspective, and then we'll continue with this discussion. So we'll take a look at the perspective of main, which there are no parameters to main. So now the question is, where do we put these two local variables? So when you first get to the entry point of main, this is what the stack looks like from the entry point, from the entry point code. This is the only thing sitting on the stack for main because the return address was pushed by the caller. Are we doing okay so far? Okay. So now the question is, where do we want to put, local variable x and local variable y? The caller cannot allocate local variables for a function because the caller does not know how many bytes are needed. Yes, go ahead. Nope. Local variables are on the stack. They're not in registers. So the way we do this is we allocate that space below the return address. So the way I usually do this now is I would put y over here and then I'll put x over here. So we have a problem because when you at the entry point of the function, the stack pointer is pointing to the return address. That's what the caller has done for you. So if I need to allocate 2 more bytes, I need to move the stack pointer 2 bytes lower in order for that to be allocated. Okay, so let's just say that we do not do anything and we just put a halt instruction here. So I don't even go to the return code because I just want to see what the stack looks like right at the entry point of the callee in this case when there are no parameters. So I can go ahead and run this code. Okay, this is going to be a shorter trace because we already had a longer trace for main to be all done. So this time we're going to focus on, by the time we get to the halt instruction, what is the stack pointer and what is exactly on the stack. So we go to the assembler and it is finishing up, I guess. Yep, give it some time. So if you have not set up Reefer Spider at this point, I would highly suggest you to install Reefer Spider on your computer. On a Mac, it might be a little bit tricky. So if you cannot get it working, I need to kind of know about it, and so I can help. All right, so this is all done. We go to the Analysis tab. By the time we get to the halt instruction, which is, oh, okay, wait, this is not. Okay, it still has the second part here, which is not what I really need. I don't know why the trace is not erasing this part here. It's supposed to. Let me try to refresh the page. No, it's still there. Hmm, that is very strange. We'll do it one more time because nothing should come after the halt instruction. All right, now it's clean. Hmm, odd. All right. So what we know at this point is the last update to the stack pointer is FF, and the last thing that we push on the stack is 09 on the stack. That is just the return address. So that means the caller is not responsible to allocate the local variables on the stack. Okay. So now the question is, okay, so we need to allocate 2 bytes on the stack. No big deal. We can just do a decrement D, and we're done. Well, the answer is yes, you can do that, but it's not a very systematic way to do things. So I personally prefer to do things in a much more systematic way. So the way I would do it, okay, which doesn't mean that you have to do it this way. The way I would do it is to create offsets from where the stack pointer should be from offset to local variables from where the stack pointer points to after the frame is all set up. So after everything is set up, the offset to local variable x should be 0 bytes from where the stack pointer points to. The offset to y should be 1 byte after x. And then the total number of local variables that I need will be the offset to the last local variable plus the size of the last local variable. So this is the way I would define the symbolic names, just so that I know, relative to the stack pointer, where do I find X? Where do I find Y? And what is the total number of space in bytes that I need to allocate for my local variables? So do we have any questions about these 3 labels? In other words, I want to set up the whole thing so that when everything is all done, the stack pointer will be pointing to the first local variable that I need to allocate, and then y is going to be, at 1 byte offset from where the stack pointer points to, and then the return address is actually going to be at 2 bytes away from where the stack pointer points to. So the key is I want this to be the picture, but in order to keep track of all the offsets, I'm using these labels. So are we doing okay so far with the purpose of the labels? All right. Now, just because you define a label that says, oh, local variable size is 2, it doesn't change the stack pointer, okay? Because labels are only visible to the assembler. It does not generate any code. It does not affect runtime behavior in any way. So that means the label is nothing more than just a handy way for me to remember, hey, tech, remember, we need 2 bytes for local variables, but it doesn't do anything to the stack pointer. So in order to actually allocate, I need explicit instructions. So in that case, I need LDI B, C, or even A is okay, but typically I try to avoid using register A if I can. So I'm going to load main LVS, to register B, and I subtract that much from the stack pointer. So this is how I allocate for the local variables, and then I use the same 2 instructions, or almost the same 2, all the way to the end, but this time I'm adding in order to deallocate those 2 bytes. Are we doing okay so far? All right. So once again, okay, lines 24 to line 25 are for allocating stack space for the local variables. And then lines 33 to 34 is doing the exact opposite, which is to deallocate the space that I have used for local variables. We good? All right. So once again we can run this program the way it is. Okay, we will just see the stack pointer changing a few times with nothing in between. Okay, but that's okay because this also allows us to just kind of take a look at how the stack pointer got changed, and then we can start to draw a picture of what is on the stack. Okay, so this is all done. We switch back to the analysis tab. Okay, it is somehow not updated. Did I save the file first? Okay, let's check. Nope. All right, do it one more time. All right, so let's go back. Okay, this is good. Um, and we have line numbers here, right? So if you add more, comments to the line number, it's actually going to be beneficial. So one thing you can do with these programs is if you take a snapshot, you can, once you take a snapshot, okay, so let's just say you take a snapshot right now. Once you take a snapshot, you can go to the source tab. As long as you're not inserting additional lines, you can actually add your comment here, and it will be reflected in the analysis tab. So I think that's one kind of really cool way to do things, because now we can say, oh, this is for allocating. So I can just change this one line here and say this is for allocating space for local variables. Okay, press the enter key. When we go back to the analysis tab, the comment stays. So this is one way to use the analysis tab is you go back to the source tab, add your comments. Okay, you'll use the // add your comments, and it will be reflected in the analysis tab. So it's easier to locate, okay, which part of the program are we looking at right now? Even though the line numbers are also here, this makes it easier. It makes it more obvious of, okay, this is what this instruction is doing. So we can see that the subtract instruction is decreasing the stack pointer, which is register D, from FF to FD. And then later on, we add the 2 back to it, so that it becomes FF again. So in between, okay, so let me just highlight all the stuff in between here. So in between, we have the stack space allocated for the local variables. This is the part where you have access, or your local variables has a space to live. In other words, this is the lifespan of your local variables. In CISP 360, did they talk about lifespan versus scope of local variables? Okay, I see some nods and some turning heads. This is one of those things. Okay, so lifespan has to do with the actual time in which the variable exists. Okay, the scope is basically referring to which part of the source code has visibility to the variable. So those two are not necessarily the same, okay? But you do need to make sure that the variable does exist in the code that has visibility to it. Okay, so one is static, one you can look at the source code and know exactly. The other one is runtime. Okay, you cannot really know ahead of time until the function is called. All right, so with this, I'm going to create a new spreadsheet for today. Okay, I go to the shared folder, which means these are the spreadsheets that you can also have access to like right away. And I'm going to call this one based on today's date, uh, 10:30. And this one is going to be a map of what is in memory. So we're going to start with location 255, and then we'll just decrement, by one, so this way, this is a consistent way that I display memory, both in the notes and also, in class. So now we take a look at this location, and for those of you who go like, but the assembler and also the analysis tab only display things in hexadecimal, well, that's okay. We can use, dec to hex as a spreadsheet formula to turn everything into, guess what? Hexadecimal. Cool. Like so. So column A, column B are basically the same. One is in base 16, one is in base 10. They just display the location in memory. We're going to use location C to indicate, the actual value, what is stored at that location. So, this is a 09. Okay, we'll just kind of use a string here to store the 09 here. And now we can use column D to say, okay, but what exactly is the 09? Well, the 09 is our return address from main back to the entry code. Okay, that's the comment. Are we doing okay so far with this part? Okay, because this was the first thing that I demonstrated. So the other two locations, which is location 254 and location 253, or FEFD in hexadecimal, those two are my local variables, one for X, one for Y. And based on the label, this is X, right? This is local variable, X of main. This is going to be the local variable Y of main. Currently, I don't know what values they have because I have not initialized. Okay. And right now, with the code that we have written so far, the stack pointer is pointing here. So are we doing okay so far? Just kind of looking at this spreadsheet here as a snapshot of what the stack looks like, with this program. Okay. So this point here is reflecting the state of the stack right after the allocation and before the deallocation. So that means, by the time we get to this instruction, this is the exact instant of time when the stack looks exactly like this. Is that okay? Are we good? All right. So the difficulty of explaining this is I have to change this picture all the time. So that means, when you go back and review the video, you can take screenshots. Okay, you can take screenshots and then say, okay, this screenshot is reflecting the state of the stack at exactly that moment when we execute the code. Yep. Mm-hmm. How does it know what? Because of the caller callee agreement. Yeah, so because of the caller callee agreement, the callee know that the caller cannot possibly have allocated the space for the local variable, and because of that agreement, the callee also knows that the last item that was pushed by the caller would be the return address. So that means at the entry point of the callee can say, I know for sure the stack pointer is pointing to the return address. So at that point, the colleague can go like, okay, let me see if I need some space for my local variables. If it doesn't need anything, okay, you don't do anything. On the other hand, in this case, main says I have two local variables. I need a total of 2 bytes. So it is the callee itself is responsible to move the stack pointer from here, which is the leftover from the caller, to down by 2 bytes so that the stack pointer is here. Is that okay? All right. So now we can go into main. Okay, we go back to the source code and we go to main and we go like, okay, so now that we got stuff allocated, maybe we can just do one of these, statements here. Okay, we want to store 67 to local variable x. So I'm going to use register, I'll use register A for the right-hand side of the assignment, which is really just 67. No big deal. But I need to now somehow store to local variable x. So I'm going to do a LDIB with a main x. So what this is doing is it is storing the offset of where I can find x from where the stack pointer points to b. It is just an offset. Okay. So the way I would document this is, this register b at this point has the value of the address of x minus the stack pointer. It has to subtract the stack pointer because it is the offset in number of bytes from where the stack pointer points to the actual location of local variable b, which turns out to be 0 because the stack pointer is pointing to local variable x. But in a very annoying fashion, I'm not, okay, that's okay. I, that annoys myself. Okay, that's okay. Sometimes I do that. But I was about to say, I'm not going to save that comment because I want you to comment the program. I want to force you guys to have to go through the program that I have written in the class and actually, annotate the program. Because if you don't do that, you cannot understand the program. Are we good so far? No? Okay. So what do you not understand? Hmm? Sorry? It's good? Are you sure? Yeah, but I saw you were using your phone a little bit where you kind of help trying to look up things related to the class. Okay. So which part are you understanding? Are you still getting the calling and the returning part? Okay. Are you understanding why we are subtracting the stack pointer by 2? Okay. So why 2? What is the 2 representing? Okay. Can the rest of the class answer that question? What is the 2 representing? Why are we subtracting 2, which is main LVS, from the stack pointer? What does LVS stand for? How about that? Yes. So did you know that? Okay, you sound a little bit hesitating because LVS is local variable size. So why are we subtracting local variable size from the stack pointer? Yep. So did you get that? Okay. Well, but then that's all we talked about. That's how we allocate space on the stack. Okay. So okay, I'm not gonna say anything. Um, so main x is an offset because main x. Okay, what is the value of main x as a label? It is 0. Okay. So we are putting a 0 into register B on line 32. And then we're going to say, but since this is just an offset from where the stack pointer points to, we're going to have to add the stack pointer back to it. So now what is in register B? We're adding 0 to the stack pointer to store it into register B. So what is register B? The same as the stack pointer, right? The same as the stack pointer. And where was the stack pointer pointing to according to the other picture that I showed you? Its location, we only have 3 choices, okay? 255, 254, 253. 253, right? Okay. So does it coincide with the address of one of the local variables? It is the address of X. Yep. Hmm? Reverse. Well, but these are not arguments. These are local variables. So you can change the ordering of the local variables all you want because because nobody else care about it. Yep. All right. So remember earlier I kind of indicate, well, I might still have that in the other file. Okay. Look at this picture here. Reg X is at offset 0 from where the stack pointer points to. Okay. So with this calculation, register B now has the address of X. So according to this thing here, I just need to store the 67 into where X is. So ST instruction will do that. Okay. Are we okay so far with this part? Okay. So if you are not, that's okay too, because what we're going to do is we're going to run it. So when we run this code, we have to remember we are now at line 31 because I don't want to run, explain everything from the beginning. So we just run it and then we look up line 31 in the trace so that we can start explanation at that point. So this is why we have River Spider and this is why we have the analysis tab is so that you can visualize the actual execution of the code and then you can go like, okay, what is happening on this line? Why are we doing this? How does this relate to the C code? Those are all the questions that would be worth answering. All right, so line 31 is right here. Okay, so we are loading 67 into register A because that is the right-hand side of the assignment. And then we move on to the next line. Okay, we are loading main X as a label into register B. Now, how do I know what value is actually put into register B in the trace? Which column? Column D, that is correct. So column D tells us what is happening to the register. So in this case, which row of column D is telling us what value got put into register B? Row 19, right? So row 19, column D tells us that, oh, okay, register B got a value of 00 as a result of executing this instruction on line 32, and the actual location of the opcode is at location 0F. That is how you read the trace, okay? So once we know this, we go like, okay, that doesn't seem very important. Why would we put a 0 into B? Because the offset is 0. So then we add the stack pointer to register B. How can I possibly know the current value of the stack pointer in the trace itself? Which row and which column tells me that? Yep, D15. Yep, the last time we update anything about the stack pointer, it is on line 25 of the source code. It was a subtract DB instruction. The opcode is located at 0C in the memory, and the effect of executing that instruction is register D became FD. So that was the last update to register D, and that's why I know register D or the stack pointer is FD at this point. Okay. So we're doing okay so far with understanding how to use the trace. Okay. All right. So that's why register B is also FD because we just add the stack pointer to 0, which is in register B to begin with. And now we are going to store, okay, what is this instruction? What does it do? What does the RTL looks like for this particular mnemonic? Okay, first question first question first. What is RTL? Do we remember what is RTL? Okay, I see people flipping through their notes. That's a good sign. It is register transfer language. Okay, in the opcode table, which column does it correspond to? Column C. Very good. So, what does STBA look like if we were to look at the RTL representation? I'll put it on the whiteboard with the reference B, and then what do we do? Sorry? Okay, so what is on the left-hand side of the equal? The reference B. Yep, that is correct. It is an assignment operation. It looks like this. So that what does that mean? So we know B is FD. We know A is 43 in hexadecimal. So what is the end result of doing this? I will try to hide that on the screen here. So what do you think is the effect of doing this, knowing that register A has 43, I think. Yep, 43. And knowing that register B has FD in it. So what is the end result? I'm hiding that cell. Yep. It changes the content of location FD to 43 in hexadecimal. Very good. So we track that operation in the little stack simulation here. And we go like, oh, okay, we know what is going here. It is 43. Is that okay? But is that the right thing to do? Are we supposed to store a value of 43 in hexadecimal in X according to the C code? What does 43 in hexadecimal mean in decimal? It's 4 times 16 plus 3. And what is that? 67. Does that sound familiar to you in the C code? That's the value that we're supposed to store in X. So therefore, these operations is accomplishing the assignment operation. So that's exactly what this is the reason why I put all of these instructions right below the C code that they are implementing. All right. So it is not easy to understand the first time, and I intentionally did not comment the code because I need you guys to do it. Okay, because if I put in all the comments, how many of you think that you are now understanding the concept? Everybody does. Okay, by the time we actually have to write code like this, I would say about 1/3 of the class still remember what that means, and the other 2/3 of the class would go like, I have no idea how to start this. Okay, but by annotating the code yourself and really understanding what is going on, and you can use this tool too, okay, to help you really look at the execution of the program, instruction by instruction, looking at the changes to the registers and also the changes to memory locations. That is how you put all the pieces together. Are we good? All right. So now we can go back here and then we move on to the next instruction, which is the next statement, which is this one here. Okay, so tell me, what do I need to do? Okay, so this is one of the things where I can give you a tip of how to solve problems in general, not just this class, but in general. You think in dependency, okay? You think in dependency, which is basically saying, what kind of operations do we have here? Let's identify those things, right? So we have an assignment operation here, which means we need to change a variable to some value. We have a function call here, and then we have another operator here. So now the question is, what do I need to do first? What is the second? What is the last thing I need to do? So think in those order. The very last thing that you need to do is the assignment. Because until you know the value of the right hand side, forget about the left hand side. You're not going to be able to do anything, right? So now our focus is now on the right hand side of the assignment. So what do I need to do to figure out the value of the right hand side? It's a function call. Okay, so what do I need to do to perform the function call? We say, okay, do we have arguments? Yeah, we do have arguments. So if you have arguments, then what do you do? This is based on Tuesday's class. When you have arguments in a function call, yes, yes. So we push the last argument first, which is also the rightmost. So that means we have to push 13 on the stack, and then we push the address of x on the stack. Very good. So this is what I call dependency thinking. You basically look at all the things you need to do, and then you draw a picture or use post-its or note cards or whatever. You just order those things according to what operation needs what. Okay, then you can determine the ordering of what you need to do. Okay, all right. So it looks like we have to push the 13 on the stack first. So that's just a LDI A13 decrement D STDA. Okay, so by this time, the line 38 and line 37 and line 38 should look familiar to you because that is how we push things on the stack. We talked about that from last week. hmm So that takes care of the 13, and now we have to push the address of X on the stack. So now the question is, how do we get to the address of X? Is there any code here that I can sort of borrow and just maybe just copy and paste to do that? How do we have we calculated the the address of X for one reason or another before this line? In order to store something into X, don't you think we needed to calculate the address of X first? So which lines are responsible to calculate the address of X? We know that we have done it before, okay? Because otherwise we would not be able to put the value of 67 to where X is supposed to be on the stack, right? So yes, line 33 is the second line, line 32 and 33 together. Okay, so we go like, oh, tech, can we just copy and paste? Sure. So line 32 the line 33, copy to the current point. Okay, and then we just push it on the stack. Decrement D, ST, DB. Because this time we're using register B. And I'm going to tell you, we got the wrong thing on the stack now. Okay, and you guys go like, how do you know? Well, yes. No, no, no. We got the right order, but we miscalculated the address of X. Okay, so the best way to do this is to run it. Okay, so we will put a halt instruction here just so that it stops right here because this is the point where we go like, hey, that's not the right thing to put on the stack. So we'll put a halt here. But before we run it, we kind of have to know what the stack is supposed to look like so that we can have a comparison. So we go here and we go like, okay, we're supposed to push a 13, which is a 0D on the stack because that's my argument, how much, right? So this is how much the parameter of the function sum or post inc. There we go. But remember, we pushed it. We did not just change the location, we pushed it. So that means the stack pointer is not here anymore. Now it's here. Okay. So if this is already ringing a bell and go like, oh, so that's why it was wrong. Congratulations, you are really fully understanding the concepts and understanding why this one little operation by moving where the stack pointer points to is going to say, oh, okay, what we just did is not going to be correct. It will be very close to being correct, but not. Okay, so what is supposed to be next? What is next is going to be the PTR of post inc, which is supposed to be the address of X. Tell me what is the address of X in hexadecimal. FD, that is correct. Okay, so we think that it should be FD, right? So we'll look at the trace. And let me make sure that we save this code and then we run it. All right, so it's about done. And then we go back to the trace. Okay, the trace goes like, okay, we can go all the way to the bottom here. It goes like, wait, that is not the right thing. It is getting FC instead of FD. What is going on here? Because according to our prediction, this is supposed to be FC, but instead it's supposed to be FD, but we got FC instead. So why is it getting the wrong thing there? Yep, yep, because the stack pointer has changed. So the 0 and 1 as the offset to x and the offset to y makes one assumption. The stack pointer is pointing here. In other words, this is the base of the frame, and all the offsets are calculated based on location FD being the base of the frame. It's not the stack pointer is not wrong. The stack pointer being here is not wrong, and now it is over here. That was not wrong. It's just that the base of the frame. Okay, let me highlight the frame here. The frame of main. This is the frame of main. Okay, and I'm just gonna highlight it with a color. So this way it stands out and we can easily tell what is going on here. So we're gonna fill it with some pukey color. There we go. Okay, this is the frame. The base of the frame is supposed to be FD. The stack pointer was pointing to the base of the frame. By the time we try to calculate the address of X, the base of the frame is actually here instead. So that means everything is off by one. Everything is one less than what they're supposed to be. Is that okay? And that is why we push a FC instead of an FD here. Now, you guys are going like, okay, all this discussion, I kind of get, but until I see it happening, I cannot really grasp what is going on. What do you think we're gonna do? Go to the trace. Yep, we go to the trace and then we look at it line by line. But this time, we execute the program backwards. Okay, you cannot do this in C++. Even with a debugger, you don't have enough information to execute a program backwards. Up to a certain point, you can, but not all the way. With this, you can execute a program backwards because you start with, oh, we got the wrong value to location FB. We got the right location to store to, but we got the wrong address to store to that location. What is going on here? So this means register B somehow had the wrong value. So you go to the last time we modified register B, which is at this point here, and this is how register B ended up with a value of FC, which is supposed to be FD. So you go one step before this. We put a 0 into register B to begin with. That was actually right, okay? Because X really is at the base of the entire frame. So the offset of X from the base of the entire frame is in fact 0. But the problem is the stack pointer. Because by this time, the stack pointer is no longer FD. It is pointing to one location below because we pushed the 13 on the stack already. Okay, that was the issue. We pushed the 13 already, therefore we moved the stack pointer to one location lower than the base of the frame. So what do we do? Well, there are a few ways to fix this problem. The easiest way to fix the problem is simply to change the offset and go like, okay, we just need to compensate for that one extra decrement D on line 37 by adding one to the offset itself. Are we getting this part? Okay. So if you're not, the time is 10:13-ish right now. So in the video, you can basically watch this part again, but replay it really slow, pause, take notes, okay? Go back to the trace. And in fact, you should be taking snapshots of the trace, as long, along, okay? Unless you know how to run the River Spider, that works too. Or you can just kind of watch the whole video. Yeah, that works too. So this is why it is off by one. So by changing the offset here to 0, 1, by adding one more, by adding one to main X, that will fix the problem. Okay, so we're gonna do just that in the source code. Okay, we did just that. So we will save the code just to make sure, and then we run it again just to make sure that this is all good again. All right, so we go back to the trace. And this time it is storing FD to the location FB, which is now consistent with what we think the stack should look like. We good so far? Okay. Are there any questions? You don't have any questions? Okay. So we got 5 minutes. Do you guys want me to finish the program, or do you want me to explain things that you want to explain further with the trace up to this point? Let me go back to the trace so you can see what the trace looks like. So do we want to look at the trace, or do we want to finish the program? Finish the program? Okay, all right, we can do that. So I'm gonna go finish up the program, okay, without explaining a whole lot because I cannot explain and finish the program in 5 minutes. So I can still say stuff, it's just not going to be, the full thing. Okay, now we can, actually call post inc. So we need to push the return address on the stack. Okay, decrement d stda, and then we do a jmpi to the function, which is called what, post inc. When it comes back, we have to increment twice. We have to increment the stack pointer twice to get rid of the two arguments that are still sitting on the stack. So that would be the caller side. And then after that, we have to use register A to update local variable Y. So we use a LDI B, cannot use A because register A has the return value from post inc. So now we use this, okay, add BD STBA. So that will finish the second statement in main. And now we go back to post inc. Okay, so post inc, I'm just looking at the time here. Post inc underscore, it has no local variables, so LVS would be defined as 0. And then after that, we define the first parameter, which is PTR. It is at post inc underscore LVS 1 plus. Even though LVS is a 0, we still have to do the 1 plus because the 1 plus here is for the return address. So that's why the 1 plus is important. And then we can now define where PTR, oh, the other one, which is how much, is at post inc PTR 1 plus because a pointer only takes up 1 byte. So that's how we define all the labels. Um, Actually, I stand corrected. Okay, I'm correcting myself. We do have a local variable. It is old value. Okay, it has 1 byte. So that becomes the new 0 at the frame. And then LVS is going to be post inc old value 1 plus. But everything else stayed the same. You can see how this method is kind of cool because it's all relative. So if I need to add something, I just have to change a few lines, and then the rest of the lines can stay exactly the same. All right, so we have to allocate the space, okay? Same usual stuff. Register B is going to be post inc LVS. Subtract that much from the stack pointer for the allocation. When we are ready to return, we have to deallocate by adding that much back to the stack pointer. And then we just use the usual return statement, which is LDBD, increment D, and then JMPB. Okay, there we go. So in between, we can now do the rest. Okay, this actually sort of goes here because it's the allocation. So now we have to implement this instruction. We have to get to the parameter PTR, get what it is pointing to, and then store that to the local variable old value. So we have LDI post inc PTR to pick a register, doesn't matter which one, register A. At AD, we get to the address of the parameter itself. We get to the parameter itself. We get to what the parameter is pointing to. Okay. So yes, as I type, I'm commenting. Okay. So you can watch the video again and just add the comment yourself. And then we have to do the LDIB with post inc underscore old value. Add BD. That is already the address. So STBA will basically accomplish this line here. And then we get to the second instruction. Okay, so this one looks a little bit nasty, but it's not that much. So we do LDI A again with post inc underscore PTR. And then we do a add AD. We get to the address of PTR. And then now we get a little bit tricky. Okay, this is PTR itself. It is by itself a pointer. LDBD, BA, sorry, LDBA B is the value that PTR is pointing to, which is what I need to increment or what I need to add by how much. So I need to get to how much now. LDIC with post inc how much. Add CD, get to the address of how much. LDCC to get to the value of how much. And then we add how much to the current value that PTR is pointing to, which is in register B. And then we store that back to whatever register A is pointing to, because register A is PTR itself. So we have to store back to where PTR itself is pointing to. And that is the second one. And now we just have to get O value back, use it as a return value. So LDI B A is fine. This is post inc old value. Add AD, we get to the address of old value, LDAA, to get to the value of old value, and that's it. That should do it. Just in time too. I'm off by 1 minute. Okay. But until we run it, we cannot know for sure, right? So we're gonna have to run it. So after we run this, we should expect x to have a value of 80, which is 50, and then y to have the same value of x, what x used to be. So let's go back to the stack here and just kind of do some changes. So we are expecting y to now be 43 after everything is done, and we're expecting x to be 50, which is the 80. So this is what we're expecting, and we go to the assemble tab and see whether that's happening or not. All right. So we see this is good. Okay. So this confirms that location FE, which is Y, is getting the old value of X. That's good. And are we seeing the storing of 50 to location FD? That's good too. Okay, because that's the X of main, which is supposed to be storing 50, which is 80 in decimal. And after everything, we need to make sure that we end at the correct halt instruction and the stack pointer is fully balanced. So the program did work the way it's supposed to. Trust me, I don't usually write this kind of length of program without making a single mistake. This is like, it's kind of like a fluke. It's like a fluke. Okay. So I can save this code, okay, and send it to you by announcement, okay. Remember, it has no annotation or very minimal annotation. You know what to do, right? Okay. And I can double check, make sure the recording is still going. So we do have everything recorded in today's lecture. So let me just send it to you first before I forget. Because anything in the temp folder is not going to be permanent. If I crash the computer right now, it's going to be lost. So I'm going to send it to you. This is called, I'll just call it post inc code. There we go. And I'll say C attached. And then attach the source code, which is temp, um, how did I call it? Sample one, I think. TTPASM. And I want to also give you the C code. Do you want the C code? Well, the C code is interleaved with the assembly code. You can easily extract it. So I think this is what you actually need. So publish. There we go. So now you have that source code. All right. Moving on to today's lab. Okay, we do have a lab today. And the lab today is, I think it's return value. Okay, so it's param and return value. There we go. So this is for today. It's already set up. You just have to access it now. It is now accessible. The access code is WTF. What the frame? All lowercase. Because that's all we talked about today was the frame. Okay, the frame has the local variables, the return address, and all the parameters. All right, so with that said, I'm